Welcome. In this explainer, we're going to break down the science behind every single impact, from a tiny tap to a massive crash. We're about to see how just a few core principles of physics totally govern the outcome of every collision in the universe.
Okay, so here's a scene we've all probably pictured in our heads. A massive truck bearing down on a small stationary car. But what really dictates what happens next? I'll tell you, it's not just about size or speed. It's about a very specific and kind of powerful physical quantity.
So, is there a rule in all that chaos? Oh, you bet there is. There's a fundamental principle of physics that actually brings perfect order to what looks like total mayhem. So, let's start right there.
All right, we're going to kick things off with a property that every single moving object has. It's called linear momentum, and trust me, it's the absolute key to understanding any interaction between objects.
So what is it, really? Well, to put it simply, you can think of it as the measure of an object's quantity of motion. It's not just about how fast something is going, but also about how much stuff is actually moving.
And you know what? It's all boiled down to this beautiful, elegant formula. P equals m times v. That's it. Momentum is just mass multiplied by velocity. Honestly, it's one of the most powerful and yet simple equations in all of physics.
So what this tells us is that both mass and velocity are equally important. Think about it. A really heavy object moving slowly could have the same momentum as a really light object moving super fast. So yeah, a heavier object or a faster object will have high momentum. But if you get an object that has both a huge mass and a high velocity, well, its momentum is just going to be enormous.
Okay, let's put some actual numbers to this to make it real. If you look at this chart, you can see it plain as day. A heavy truck at high speed has just vastly more momentum, more quantity of motion than a lighter car. And that huge difference right there, that is exactly why stopping the truck is such a massive challenge.
So, okay, an object has momentum. Now the big question is, how do you change it? Well, the answer lies in another key concept, and it's called impulse.
Now, here's the crucial point. When you apply a force over a period of time, you create something called an impulse. And that impulse, it's exactly equal to the change in momentum. So if you want to change something's momentum, you've got to apply a force over a certain amount of time. Simple as that.
All right, let's put this into practice. Imagine you've got a 75-kilogram person just sitting at rest. Then their car accelerates to 6 meters per second in just 0.6 seconds. Okay, so their momentum changes, right? We can calculate that change. That's the impulse, and it comes out to 450 kilogram meters per second. Now, since we know impulse is also force times time, we can figure out the average force the seat is pushing on them with. 750 newtons. That's the force needed to get them moving.
Okay, now we've arrived at the golden rule. I'm talking about the law that governs literally every interaction in the universe, from billiard balls on a table to entire galaxies colliding.
And this is pretty profound, actually. What it means is that in what looks like the total chaos of a collision, the total amount of momentum before the crash and after the crash is exactly the same. It's perfectly preserved.
So here's what that looks like in the language of math. The total momentum before the collision, that's the whole sum on the left side there, is exactly equal to the total momentum after. Now sure, momentum might get sloshed around within the objects, changing their individual speeds, but the grand total for the whole system, it stays constant. It's perfectly balanced.
Okay, so now that we have this unbreakable law in our back pocket, we can start to explore the two main types of collisions, and we'll start with the ones that bounce perfectly. So, in what's called a perfectly elastic collision, the objects rebound without losing any of their energy of motion. You've probably heard of it. It's what physicists call kinetic energy. It's just the energy an object has simply because it's moving.
Yeah, this is like the ideal perfect collision. Not only is momentum conserved, but that kinetic energy we just talked about is conserved too. The objects don't get damaged, they don't generate heat. The absolute perfect example is watching two billiard balls click off one another.
But what about most real-world collisions? Like car crashes where things are definitely not so perfect and clean? What happens then?
Well, that brings us to inelastic collisions. And this table right here, it shows the single most important difference. I want you to notice that momentum is still conserved. That law is unbreakable, remember. But look at kinetic energy. It is not conserved. It gets transformed into other things, like the sound of the crash,
the heat from friction, and, most importantly, the energy that's needed to bend and deform all that metal.
The most extreme version of this is called a perfectly inelastic collision. And as you can see in the diagram on the left, this is where the two objects literally stick together after they hit, moving off as a single combined blob. That car crash on the right, that is a textbook real-world example of this, where all that tangled wreckage moves as one piece right after the impact.
And this is where it gets really cool. Because we know momentum is conserved, we can predict the outcome perfectly. So we start with our system, in this case, two freight cars. We apply that unbreakable law. Total momentum at the start equals total momentum at the end. Then we do the math. We set the initial momentum equal to the new combined mass times its final velocity. And the results? We can calculate their final speed with complete and total accuracy. It's amazing.
Seriously, this one single formula is all it takes. It lets us predict the final velocity for any two objects that smash into each other and stick together, just by knowing their starting masses and velocities. All that chaos from the collision, suddenly, it becomes perfectly predictable.
And hey, what about that kinetic energy that went missing? We can calculate that too. In one specific car crash scenario that was studied, a whopping 38% of the initial energy of motion just vanished. Well, it didn't really disappear, did it? It was instantly transformed into the sound of the impact and all the force needed to permanently bend and crush all that steel. That is a huge amount of destructive energy being released.
And look, these principles have some seriously powerful real-world applications. Take the ballistic pendulum, for example. To figure out how fast a bullet is, you fire it into a block that's hanging from a string. It's a perfect example of an inelastic collision. Then, just by measuring how high the block and bullet combo swings, you can use the laws of conservation of momentum and energy to work backwards and calculate the bullet's original speed. It's an absolutely ingenious use of collision physics.
So, from now on, every time you see a car's crumple zone designed to absorb energy, or you watch a rocket propel itself by pushing gas out its back, you're seeing these very laws at work. This physics is happening all around us, all the time, governing every single interaction and keeping the entire universe in this beautifully predictable balance.